around the park. So what is the reason of sometimes I give you a quiz that's so superficial? Some of you, a handful of you, come to me and are concerned with the test score for test 2. Obviously, you know, it wasn't an easy test. So I'm repeating myself in the first lecture. Come time for the final grade, you are between B and B minus. Mine and I'm going to consult each other and say, the first question I ask is the student, you know, come to the office hour or make an effort to learn the material, and does he or she, you know, turn in all the homework, and does he or she done all the quizzes? That tells me when you are or not in class. Now, if you are at one point on the borderline between a B and a B minus, and if you have done all the homework, turned them in, and you've done all the quizzes, most likely will say you deserve a higher grade. I didn't tell you anything different from the first lecture. I cannot change the grading scheme now, it's way too late, it's a contract that we signed. But those are the soft points that you can earn. And that's some time I give you quizzes that, I mean, this quiz will take you 3 minutes to do, honestly. But it tells me whether you're independent or you are trying and you deserve to have a higher grade than otherwise. Is that clear? All right, and is that fair? I mean, I think, you know, it's not perfect. It's a system that I don't like to drill on it too much, but, you know, we have no choice. Okay, so with that, today, we're going to start a topic called kinematics, but the agenda is that I want to make sure there's no question on the 2 previous set of homework. Solution has been posted, but I just want to take a question if there is any. If not, we're going to look at what we meant by velocity and acceleration fields. You know, what does that mean? You know, what does that entail and how it relates to what we're going to study? And then I'm going to pause and you know, rework problem 3 and 4 from test 2. I'm going to give you all the specifics so you can rework the problem for those who didn't get it right correctly. And then beyond that, I'm going to start what I call a differential equation, DE, for continuity. It's a little bit involved, take a lot of intricate setup, but you see it once, you get more comfortable on how one can develop some differential equations so you can do very, very small, tiny element analysis. And for any problem that I throw at you, right, an automobile, nuclear power plant, heat exchanger, gas turbine engine, they are well beyond control volume backup envelope calculation. And that's what your career will be if this is what you do. And then at the end, 5 minutes, I give you the quiz. Any question before I start? Homework, rework, test 2, problem 3 and 4, and plus 2 problems that has to do with what we're covering today in the lecture, kinematics. And they're old edition, so Mike will post those statements so you can have them to work on. Problem homework for next Tuesday is still a little tentative. My intent is trying to actually cut back on the homework because we are now towards the back of the semester. I front-loaded it so that I work you crazy, and now I'm giving you some slack. You can catch up on another homework. All right, so homework is more like 1.5 hours, maybe almost 2 hours. We are doing very well in terms of our scheduling, and the very last week of the lecture, actually we'll go back to chapter 2, something called hydrostatic. And that is kind of the finishing touch for the entire semester. Okay, so let me get the 4 started for any question on any of the 4 homework that I haven't time to cover. One is the race car with the upside down airfoil. Another one is the parachute, all of which just has to do with looking up the right drag coefficient. And then we have also the use of those formulas for a very limited application of a flat plate, geometrically very boring, but as with low pressure gradient, and incompressible, and laminar. So with those conditions, you have some very nice formulas to estimate the thickness of the boundary layer, like the car hood, and the shear, right? Those are very basic concepts. No question. Good, okay, I didn't expect any. So, kinematics, you probably have seen this in other classes, which means it doesn't involve any forces. All right. Once we involve forces, it's called dynamics. So you have particle dynamics, we have fluid dynamics, meaning force need to be accounted for. But right now, we are mostly concerned with just velocity and acceleration description. So in fluid mechanics, because of the shear and continuous deformation, unlike a particle or a deformed subject we study from sophomore, it turns out there are different references or viewpoint or description of the acceleration and velocity due to those characteristics. So the best way to illustrate that is by an example of tracking traffic on a highway and be able to describe that intelligently. So a person who receives that information know what you're describing and what you are referring to. So let's say we are looking at traffic pattern between two exits on I-81. Say between Christiansburg and the exit Virginia Tech. I think, I'm not sure. Exit 118, you know, that's also the exit number to UVA. Yeah, at Charlotte School, what a quickly coincidence. Right. Okay, so here is a pattern where for conventional particle dynamics, most people will use this description of what I loosely refer to the name as Lagrangian particle dynamics. You may have heard of that higher. And what that refers to is to describe the traffic pattern between these two exits. I will follow one and only one car A. As it go into my space, I will describe to you for this particular car. So Lagrangian is following car A. I will tell you for this automobile, which path is it going? From exit 118 to exit 123. And during that path, what is the speed of that vehicle, and as well as acceleration and deceleration, if any. And if the vehicle takes a different path, I will track it and tell you exactly at any instant in time what that vehicle is doing in terms of direction of the vehicle, the velocity, acceleration, etc., etc. So it's only tracking one particle, one vehicle. And that's very conventional. That's something that you're accustomed to. Your particle dynamics is all based on that concept. So let's describe that first. A traditional way of looking at velocity and acceleration field. So, and that we call that the Lagrangian. So that probably is nothing new. Maybe perhaps just the name of Lagrangian wasn't described to you or referred to as such prior, but you are familiar with this type of description. It's no different than I take this eraser and I toss it up and watch it come down. I tell you where it is, what velocity, what acceleration. That's particle dynamics. Very conventional description of the velocity and acceleration field. There's one problem. Fluid, as we know, is deformable continuously. I have a shear, the fluid particle will continue to shear and doesn't follow a rigid body dynamic. because of that, this description due to the Lagrangian is not very practical. So I'm not following a rigid car, but instead, entire domain in this highway, except the highway can be deformed due to shear, and tracking one particle by itself is not very convenient for me to communicate or describe to you how the velocity and the acceleration field changes. So I need to invent or come up with a different description, and that is called the Eulerian description, of which instead of following one particular car as it comes into exit 118 and leave at exit 123, I'm actually focusing on one point in space. I call it point B. At this point, B, I'm going to describe to you over here at point B, this one fixed space. I'm not going to tell you any specific cars like I did with tracking car A. Instead, I would actually look at that point, when there's a car come by, what is the average velocity of that car? And how many cars come by that point per hour, so I can describe to you in space what is happening in that particular location of this segment of the highway. That is what we call an Eulerian description. And that has some interesting consequences, which I will show you momentarily. But right now I want to pause and make sure, let me dictate for you what is meant by Eulerian. And then I want to make sure you have time to digest the differences between these two, namely two different references of describing the event that happened between each two exits. So the Eulerian is more applicable to fluid dynamics, fluid mechanics, due to the continuous deformation. And what we meant by Eulerian is now we're not describing a particle, but instead we're talking about the velocity in the field, in the whole domain. The point B is just one example, but to fully describe the whole events between the two exits, I have to basically tell you every point on this space. And that is a velocity V now having 4 dependent variables, meaning there are 4 parameters that will determine this velocity V, which is give me the coordinate, where are you located, and give me a time. What time are you referring to? So in the highway example, obviously you only have 2D, but in actual fluid application, an airplane or an automobile, you have both X, Y, Z coordinate and the time. So instead of particle, this car of a BMW coming in and out and tell you the path that it takes, the acceleration, the velocity, I'm telling you the velocity at one point. And by describing every point between the two exits, you should know what the traffic pattern looks like. Yes?
So is this basically just the idea of like a control volume, looking at a region that's
Kind of.
specific?
Kind of. Now we are now diving into the control volume in detail. That's one way to look at it. Before, in control volume, we are mainly concerned with the inlet and the exit. And now I have to really dive into exact control volume space to describe to you what is the acceleration, what is the velocity. Once I have that nomenclature laid down, then I can start deriving the continuity equation for you. Right? So this is just a very basic fundamental concept that we have to get ingrained to click on the next step. Yes?
With Eulerian, are you also describing the acceleration field?
So the question is, for those in the back, on Eulerian, will I be next describing the acceleration field precisely? That's the next step. And that resulted in some very interesting consequences, which you have seen before by way of the Euler's equation of motion, and now we're coming in full circle. And I will dive into that momentarily. The only difference is back then we only limit ourselves to the streamline coordinate, S and N. And now we're going to do the same thing, acceleration in 3D, X, Y, and Z. So, fair question, that's the next step. But right now I just want you to appreciate the difference between the two frame of references and why. And why. All right? So let me finish this, though the so-called Eulerian is where now I have for the first time a full field that look or sound a little unconventional, but indeed for practical reason due to the continuous deformation, this may be a better way to describe the events that happen between the highway traffic. So instead of a particle that I'm fixing my focus on, now I'm focusing on a fixed point in space. And because of this, I will have to have a different set of equations for velocity and acceleration. The question is, what would they look like? That's the next topic. But this concept between the particle description of identifying an automobile versus now we look at a fixed point in space, essentially. Fair enough? So with that, my velocity field, not referencing to that highway traffic now, but in general three-dimensional problem that we will encounter in engineering practices. So I have X, Y, Z coordinates. Now we're generalizing the problem to a Cartesian coordinate, X, Y, Z. Whereas prior we have streamline coordinates. There are other coordinates resulting in other formulation like cylindrical or spherical, but that's beyond our coverage. And just to revisit the nomenclature, this will be used for the next few lectures. Repeatedly, IJK with a head. Anyone know what that means? Univectors, very good. So the head just means univector. That tells me the direction. I is the one in the x direction, and so on and so forth. Our nomenclature for velocity, U, V, W in the x, y, z direction. That's our moving forward nomenclature, which we have seen before. Sometimes I will also use Vx capital, Vy, and Vz interchangeably. So I hope you are versatile enough to be able to mix those nomenclature. So the cap V now is not volume, but rather velocity in each of the directions. So what I have to do is to, at a fixed points in space, now describe to you this velocity vector V, which has a function of 4 independent variables. I hope you know what we meant by independent variables. We beat that to death in dimensional analysis, right? Meaning that the velocity field on the left is uniquely and unambiguously determined if you're going to tell me the x coordinate, the y coordinate, and the z coordinate and time, all right? And hence those are called independent variables. That now has 3 3 components, one in each direction. So that's now our so-called velocity field in 3D, whereby you have to give me 3 coordinates and a time. And from then I will tell you each of the velocity component in each of the direction, so that you know any point in my domain, in my full field, I know the velocity unambiguously. That's the easy part. The next part is the acceleration. Any questions so far? Because of this dependency, this change in how we describe the full field, the acceleration take on a very interesting twist. So now my next step is to describe in this x, y, z 3-dimensional coordinate, what is the corresponding acceleration due to this velocity field. And to do it kind of as a motivation of this very somewhat dry new description of the field, let me set an example which we will work on after I introduce acceleration. This problem involves flow along a nozzle. From left to right. Overall length of the nozzle is L. X direction is positive pointing to the right. And the velocity field given by this nozzle is a function, linear function of x. Right? So what is the problem about? I'd like to know 2 things. At the exit of the nozzle, what is the acceleration? Number 1. Number 2, how long it takes. For a fluid particle, how long it takes for a fluid particle to transit through this axisymmetric nozzle, cylindrical nozzle. So we will tackle this problem after I describe the acceleration. But just on the problem statement alone, given the velocity as shown in here, can you tell me if this problem is steady or unsteady? Just by looking at the given velocity. How can you answer that part? Yeah.
Time isn't one of the variables, so it's probably gonna be the same for all time.
There's no time term on the velocity field, so without making any assumption, whether it's from the problem statement, this is a steady problem. No time dependent term. That's a good observation. That it's not an assumption, it's a given, but you have to observe it. Do you agree? What is the velocity in the J and K direction with this given velocity in the problem statement? There's 0 because it's nothing. Nothing in the Z and Y direction. So this becomes, yes?
So as we look at this is like funneling it down. So isn't there technically like along that boundary, isn't there like a Y component to it? Or a Z component to it?
That's a fair question, yeah. The question being raised is because the flow is converging, will there be a component perpendicular to the x direction? Yeah, that is actually a very good statement. We are neglecting that because the majority of the flow in the axial direction is much greater than that in the other direction, and hence that is in the problem statement being neglected. So they're small enough that I don't even pay attention to them. But actually, in the physical sense, you're correct. The flow, because the shape of the nozzle will have to have some element that go towards the center, but usually they're pretty small. Fair enough? Yeah, good observation. But as given in such here, those terms are inconsequential. All right? So this becomes a 1D problem. The 1D problem. Now, is there any acceleration? It's a trick question. Is there any acceleration?
Yes.
But it's steady.
It's not.
It's steady. I can't have acceleration if the flow is steady. The acceleration comes from the shape of the nozzle. It happens in space. How do you know the flow is accelerating? I only want to hear one word start with letter C. Continuity. You've seen this before in the Euler's equation, differential form. You may not remember. But we're coming now back at it with much more sophistication in 3D. So before I can tackle the acceleration, somehow, somewhere I have to develop a new concept of acceleration from this Eulerian description. The traditional particle dynamic sense of acceleration is rate of change of velocity with respect to time. On that basis, you will say that nozzle has no acceleration. But you're wrong. So I have to alter this by way of something called, from your calculus, the chain. What do I mean by that? Knowing that there are four independent variables, 3 coordinate system and time t, the acceleration will have to be broken down by the chain rule so that I look at all possibility of acceleration both in time and in space. That is the consequence of so-called chain rule, which I take each of the independent variables and look it up. But if you add them up, it gives you the same acceleration as we know it in the past. So that can further be simplified. If I were to rewrite this equation, what can you tell me about du dx, rate of change of x distance with respect to time? What does that amount to? U, yeah, very good observation. U. And v for y. And w. For z. So now I have a very interesting acceleration, which I will block it up into 2 pieces. The first one is very conventional. I call it local, at a point, local acceleration. And that piece will be 0 if the flow is steady. So from the statement of the problem on the left, that nozzle being steady, I will have no local acceleration that is time dependent. That is 0. The term in the bracket now has some very interesting physical interpretation. we're gonna call that convective. Convective, meaning it moves with the flow, convect. Or spatial, or because it comes about due to changing in space from inlet to exit where the area is smaller. Acceleration. And the physical interpretation of this when the flow goes through a device that the geometry is changing. Due to the shape, when I move from the inlet on the left to the exit on the right on that nozzle, I am moving through a region of changing velocity. In this case, the velocity is speeding up. And because of that, I will have an acceleration due to the spatial reference from inlet to exit. So this Eulerian description now created a very particular and very unconventional acceleration that we use the capital D to remind us that moving forward, we call this total acceleration, and sometimes in some text, it's also called substantial acceleration, and mainly that it has two pieces to it. The conventional piece, time-dependent, you're very familiar with. The second term in the bracket, spatial acceleration, is totally new. And that need to be accounted for by us in fluid analysis. Can you see the difference? And now we can use this tool to solve this nozzle problem. Let me use the board in the center. So the problem statement already tell me is one-dimensional and steady. And now to make use of this total acceleration, let's see what we can simplify in reference to this problem. And that's essentially your homework, is to make advantage of this new concept of spatial acceleration to define a flow field. So I'm now taking this equation that we just derived and apply that to the problem for the example. So what can I simplify based on the problem statement? What happened to the first term? Because steady state. Look at the velocity field description. Is there any term for V and W in here? What is V and what is W? Based on the definition of the velocity that was given to you. There's zero. It's one-dimensional. So my subsequent acceleration had only one spatial component, and that's in the x direction. All right? So now I just have to substitute with the problem statement that u is given as a linear function of x. So to get this convective acceleration, I have to do a partial derivative of the velocity u with respect to x. And that's a very simple calculus exercise. Velocity unchanged. How do you differentiate this equation with respect to x? What will be left when you differentiate this with respect to x? Is 1 over L with the velocity in front. So my convective acceleration after simplification is given by this equation. And now I can substitute the coordinate x at the exit. So when x equal to L, the equation become two times velocity squared divided by the length of the nozzle. And the unit works out is in meter per second squared. So no time dependent acceleration, but yet I have a convective acceleration. Part B is a bit more intriguing because now I have to integrate. Why? Because I'm asked to travel from inlet to exit over length L, what time it takes to reach that. And if I work out the velocity in the x direction, I'm stuck with this differential equation. And remember, the velocity is nothing but just dx dt, or to get the time, I have the velocity in the denominator, right? So to get the actual time it takes to travel through the nozzle, involve the integration. Anyone recognize the integral of the dx over something of x in the denominator? What would that result from? ln, natural law. Very good. So I will give you the result, and if you have problem visualizing that, you can differentiate the result and convince yourself that indeed it gives you the same differential equation on the left. So the integral of dx over x resulted in a natural law. And now I have two integral limit, inlet to the nozzle, and the exit, resulting in a time that is a natural log of 2. It is also a function of the length and the velocity at the inlet. So that's a very elementary, somewhat simple example, kind of help to gel this together. But the main takeaway is, even though the flow is steady, you still have acceleration. When did you see that before? Have you seen that before? Where? Let me repeat the question. Under what section have you seen a case where the flow is steady, but I can have acceleration? Differential equation of the Euler's, right? Where we actually went through the same long and dense, except back then it was really simple because we are only dealing with the streamline coordinate. Now the v vector is in 3D, x, y, and z, and the acceleration itself also is in 3D. So all we've done is to generalize it, so I have a tool that can solve any problem, not just a streamline. You throw me any problem, I can tell you the velocity, acceleration, field. That's the difference. So armed with that, we are almost ready to start deriving an equivalent or cousin of the continuity equation for now a tiny element. Yes,
In the fluids world, do higher order derivatives matter in many cases?
it does, depending on the problem, and sometimes this question is kind of a little bit over our head. The question is, in higher order term, like this is first order derivative, you will later on see something like this. That's coming. This is higher order term. Is that important? The answer is yes. At times, we can make some very clever approximation to neglect them. And that is what we'll do towards the last week of the semester, so-called the boundary layer analysis. It turns out if you're clever, you can neglect them by making some very, very good approximation. So that question will come. Okay, let me give you a 2 minutes break so I can erase the board and start with the test 2 discussion.